Hello everybody. Today we will merge exponential and Poisson distribution in queuing systems. We'll analyze, assuming that we have in the queuing system as follows. We have customers' arrival in Poisson process or distribution with rate lambda, and service time is exponential distribution with rate mu, and the departure time is also Poisson process with rate lambda. If we have this assumption, we can solve this model, okay, in accurate way. Okay, we'll prove that in this lecture. We'll prove that our assumption is correct. It's good for modeling this queuing system. Okay, let's go. Example by example. We'll prove it by example. So we have given data arrival time of customers n at in different time, and Sn service time of customers number of Sn. In this lecture, we focus only on arrival time and service time. In this lecture, no queuing time or waiting in the queue system, queue list, okay? So we focus only arrival and departure, service and departure later. So we'll now make modeling of arrival process. Tn, it's time between arrival, n and n minus 1. So the general formula here for 81, 2, 3, 4, 5, we make the difference to get the difference between each customers. Tn is the difference between each customers. So Tn equal arrival time n minus arrival time n minus 1. So it's the difference between two consecutive customers. T1 between first customers and 0, where customer 0 equals 0, and so on. T2 equal customer time of customers 2, arrival time of customers 2, minus arrival time of customers 1, and so on. Okay? So we have this. If we have number of events, Poisson process with rate lambda, conclude that, and bidirectional that, the time between events is exponential with mean 1 over lambda. We will prove that. So if the number arrival is a Poisson process, then the difference of times for each customers or for each event is exponential. Okay, so we'll prove that. From that, we can conclude, or we can calculate the average time between arrival, here called T bar, or we can write it T average. So the T average equals summation of all Tn over n, like we did in last lecture. Then the arrival process is a Poisson with rate lambda 1 over T. Okay? Lambda chapeau or hat, this, don't include it. Just write it lambda 1 over T. T average here. Here we have T average. So lambda equal 1 over T average. Okay? We have example here. We have 20 customers arrives in different time, and service, this is the service of each customers. So assume our modeling like we did, assume Poisson arrival and implies or bidirectional exponential interval time. So from the previous equations, the time average equals summation of all Tn over n, so equal 3.735. And lambda will be 1 over T equal 0.268 customer per minute or 16 customer per hour. Okay, this Tn here, we have here Tn, we must make the difference here, okay? So Tn, we must calculate it, T2 equal 2 minus 1 minus, 2.1 minus 1.4, okay? T3 equal 5.4 minus 2.1, and so on. And sum all the Tn's divided by n customers give us this value. Then we calculate lambda 1 over T equal 0.26. Okay? Any question here? Good. Now, we'll go to another side. So for the server side, the same modeling service process. Number of events, Poisson process with rate lambda. So the time between events is exponential with mean 1 over lambda, the same. If service time is exponential, then departure time must be Poisson process. So service time is here is exponential, and departure time is a process. Departure time is a process. Okay? So for the same example, we conclude that average service time equal summation of Sn over n equal 4.595. The mu expected arrival rate, mu, equal 1 over T equal 0.2 or 12.1 customer per hour. Okay? Here, I will go back. We have here Sn. Okay? We sum all the service time for each customer. We sum them all and divide it by 20. Okay? Here to get 4.59. Then the mu, which is service time, expected arrival rate, service time or finish rate, not arrival, finish rate, lambda 1 over 4.9. Okay? So, all that to calculate the variance. And we prove it by variance. Focus on this slide. Number of events, the same Poisson process with rate lambda, gives us, if we have Poisson process, must we have the mean value, the expected value equals the variance, or the bidirectional. If we prove that the mean value of any model equals the variance, so we have Poisson process. Okay? So if we have this, we have that. Or if we have that, we have this. Okay? هم تنتبهوا هلا حنبرهن هيدي من الكالكوليشن من الارقام اللي عملناها بالاكزامبل اللي ورا we prove that mean value equal variance, so we have system in Poisson process. Okay, let's go. Now, if expected time, arrival time, which is equal now summation of Tn over n, it's approximately equal. It's not exactly equal. It's approximately equal to variance, standard deviation of Tn minus T bar square over n minus 1. So that's why Poisson process is good to model the arrival process, because we have the mean value approximately equal to standard variation. Okay? That's why the Poisson process is good to model. And also, the same for expected value of service time, summation Sn over n, approximately equal to summation for the variance. Okay, so also the Poisson process is good to model the service process. Okay, we can use a Poisson process in arrival process, even in service process. Okay, example result. From the result before, we have arrival time T average equal 3.7 and the standard deviation radical 16.22. 16.22 اجت من وين اجت هون؟ من هون. وين لحظة، وين 16.2 في هون لاندا 16. اوكي، من الايكويشن هي summation tn minus t average على l minus 1 سكوير راديكال، طلعوا انه تطلع راديكال 16.22 equal 4. So as you can see, the expected value approximately equal to standard deviation 3.7 around equal 4.0. Okay, so Poisson arrival process with rate lambda equal 1 over t 0.268. And for the server side, average service time S bar equal 4.595. And from the equation before this equation, Sn minus S average square summation over n minus 1 radical square to get 20.26 radical equal 4.5. As you can see here in the service time, approximate equal here 4.59 equal 4.5. So okay, as you can see, so Poisson service process with rate mu 1 over S 0.202. So why we calculate this? Because we want that all this lecture, all this calculation to prove another proof that if we have average expected time equal to standard deviation or variance, so the Poisson arrival process or Poisson service process is best for modeling Q. Okay, another proof is graphical proof. Now we prove that in graphically. Okay, if a process is a Poisson with rate lambda, then the plot of for each customers and its arrival time and ATN will follow the average lambda t. If this distribution, if the customer's arrival time, random customer's arrival time, follow the line lambda t, so we have process Poisson. We can calculate, we can evaluate, manipulate our queuing system using Poisson. Okay, Poisson distribution. Okay, so the steps we want to do it now. We want to plot an ATN where X is the time and Y is the customer's number, and find expected value of T and call it lambda, and draw again the function Y equal lambda T. If the plots close to the line, so we can modeling our queuing system using Poisson process. So this is another proof that the Poisson process is the best to model our queuing system in the next lectures. Okay, so we have the same example before. 20 customers with arrival time. Okay, so already we calculate T average 3.7, lambda equal 1 over T 0.268 customer per minute. Now we want to plot an ATN for each customer's its value. This is X axis, and the customers will be Y axis. Okay, And also we want to plot y equal lambda t, which is lambda here, calculated from these values. Okay? If it's are closed, so it's true. I will prove that the Poisson process is the best for modeling our queuing system in general. Okay? So as you can see, from the time axis here, for each customers arrive in different times and different events, as you can see. We have here group, nothing, group, nothing, group, nothing, group, nothing. So this is events, between events, okay, is a Poisson process. Okay, as you can see, they are this distribution of arrival, they are close to lambda t. So for best modeling here, we prove that the best modeling is Poisson process. Okay, this is our lecture today. Small lecture, but effective to prove that Poisson process modeling is the best choice to solve our queuing system later in the next lectures. Okay? Any question here?
No.
Any question? Do you have any questions? Okay, I will stop the recording. Okay.